High in the night sky shines Betelgeuse, a giant star so unstable it could explode as a supernova within our lifetimes. Its fading brightening and strange pulsations have baffled astronomers for years. Today we'll uncover what might be happening inside this colossal star. If you enjoy the journey, please like, subscribe and share, and tell us in the comments, do you hope to witness Betelgeuse go supernova someday? Thank you for watching. Now let's begin. On a quiet night, the sky above Earth stretches out as a dark dome scattered with points of light, a scene that has changed little over the span of human history, even as the understanding of what is seen grows more precise and more careful. The planet turns steadily beneath this canopy so that constellations rise and set, but the broad impression remains one of a soft speckled darkness, in which bright stars, faint stars and diffuse glows all share the same vast stage. Far from city lights, the band of the Milky Way arches across the darkness, as a hazy river of light, pale and gently structured, suggesting to the eye that there is more in the sky than individual stars alone. This band is not a cloud in the atmosphere, but the combined glow of many billions of distant suns spread through a flat rotating system of stars, gas, dust and invisible matter that astronomers call a galaxy. The Sun and its family of planets, including Earth, sit within this system embedded in one of its spiral arms, so that when an observer looks along the plane of the disk, the sight line passes through dense layers of stars and interstellar clouds that blur into a continuous radiance. Viewed from very far away, the Milky Way would appear as a barred spiral with long arms curling outward from a central bulge, but from within only the cross-section of this structure is visible as the faint luminous band. The darkness between stars is not empty, even if it seems so to the unaided eye. Sparse gas, thin dust, and the far more elusive presence of dark matter all contribute to the mass of the galaxy, shaping its rotation and the slow evolution of its form over timescales far longer than the entire span of human civilization. Individual stars trace wide orbits around the galactic center, completing one circuit in a period of several 100 million years, moving together like scattered lights embedded in a great slowly turning disk. From the ground, this motion is not directly seen because the human lifetime is short compared with the time a star takes to drift noticeably against the background. Instead, the stars appear fixed in patterns that cultures across the world have named and re-narrated for many generations. Some of these patterns are recognized internationally as constellations' official groupings that astronomers use as a map to divide the sky into regions. Each region contains many stars at very different distances arranged into shapes that are meaningful only from the particular vantage point of Earth. Behind these patterns lies the great depth of the galaxy itself. Along any given line of sight, the light from nearby stars mixes with the light from more distant ones, as well as with the faint glow of diffuse gas clouds that scatter and absorb starlight. Some regions are bright with clusters of young hot stars that form together from collapsing gas clouds. Other regions are marked by dark lanes where dense dust clouds block the light behind them and carve out soft irregular gaps in the Milky Way's glow. The night sky is therefore not a simple flat picture, but a three-dimensional structure in which distance, brightness and composition all combine to produce the patterns seen from the ground. Sensitive instruments carried on telescopes on the ground, and above the atmosphere reveal this structure in many kinds of light, beyond the narrow range that human eyes can detect. In radio waves, long filaments of cold hydrogen trace the spiral arms. In infrared light, warm dust and cooler stars emerge where visible light is heavily blocked. In ultraviolet and X-ray bands, energetic processes near very hot stars and compact objects light up the galaxy in harsher colors. Yet even with these tools, the most immediate experience remains that of the sky, as seen without aid a quiet high dome, where the Milky Way lies across the darkness, and brighter stars pick out rough shapes that repeat season after season. As Earth orbits the Sun, the night side of the planet faces different directions in space at different times of year, so that some constellations are seen in one season and replaced by others in another. This steady change unfolds with the slow rhythm, giving each time of year its own familiar set of stars. Over many months, the orbital motion carries the vantage point around the Sun, allowing different sectors of the galactic disk to be seen at night. Over even longer intervals, the slow wobble of Earth's rotational axis gradually shifts the alignment of the seasons with respect to the stars, so that the exact pattern of the sky on a given date changes very slightly over thousands of years. Against this moving backdrop of subtle cycles, the Milky Way itself remains a constant presence, a reminder that the local patch of sky belongs to a much larger structure. In one direction lie the densely populated central regions, rich in overlapping star clouds, and crossed by thick dust lanes that dim and redden the light. In the opposite direction lie the outer parts of the disk, where stars are more thinly spread, and the band of the galaxy appears narrower and more fragile. Everywhere within this disk, stars are born live through long stretches of time and eventually reach the ends of their fuel supplies. Some are small and faint, others large and luminous, and together they give the Milky Way its varied appearance. From the ground, only a small fraction of these stars are bright enough to see individually. The rest blend into the general glow that gives the band of the galaxy its milky character. Still, the light from every visible star and from the diffuse background itself has spent long periods travelling through space before reaching Earth's atmosphere. Even light from relatively nearby stars has been on its way for dozens, hundreds, or thousands of years, while light from more distant parts of the galaxy has travelled for tens of thousands of years. The night sky seen at any moment is therefore also a record of different times in the past, with nearer stars seen as they were in more recent centuries, and farther structures seen as they were in far older epochs. This mixture of times and distances is woven into the simple overhead view that appears so calm to an observer at the surface of Earth. From this vantage point, the sky can seem almost unchanging from night to night, yet the galaxy it reveals is dynamic on its own enormous scales, with stars orbiting, gas clouds drifting, and spiral arms slowly turning. The wide night sky, with its faint river of the Milky Way and its scattered bright points, is the broad frame that surrounds every individual star and gives each one its place in the galaxy. On the same dark canvas where the Milky Way stretches as a faint band, one particular pattern of stars draws attention, season after season, a loose but recognizable figure that astronomers call Orion. This constellation lies in the direction of one of the Milky Way's spiral arms, so that when an observer looks toward it, the line of sight passes through a busy region of the galactic disk. From Earth, Orion appears as a roughly rectangular shape with a short straight line of three bright stars cutting across its middle, a pattern that stands out clearly against the softer background. The stars that define this figure do not form a cluster in the strict sense, since they lie at different distances along the same general direction in space, yet from the vantage point of Earth, they trace a coherent outline that remains stable over many human lifetimes. Their light has been travelling for hundreds or even thousands of years, each star contributing its own hue and brightness to the overall impression of a distinctive patch of sky. Orion sits near the celestial equator, the imaginary extension of Earth's equator onto the sky, so it is visible from a wide range of latitudes in both the northern and southern hemispheres. This position makes the constellation a familiar marker for many cultures, since it climbs high into the sky for a large fraction of the world's population during part of the year. In the northern hemisphere, Orion rises on long nights, when the air tends to be cooler and clearer so its pattern can appear crisp and sharply defined. In the southern hemisphere it may appear tilted at a different angle, yet the basic arrangement of bright points remains the same, anchored by the 3 central stars that mark the belt, and flanked by brighter stars at the corners of the figure. These stars are not all of the same type. Some are hotter and more luminous, radiating strongly in blue and white light. Others are cooler and larger, glowing more strongly in red and orange tones. Spectroscopy, the study of the way stars spread their light into a spectrum of colours, reveals that Orion's bright members include young, massive stars that burn their fuel rapidly, as well as stars that have already moved beyond the simple stage of core hydrogen burning. Many of the stars in and around the constellation belong to a larger complex of star-forming regions that stretches across this part of the Milky Way. Invisible light parts of this complex appear as glowing clouds, threaded through with dark lanes, while in infrared light the dust that obscures many regions becomes more transparent, allowing astronomers to trace the structure of the gas and the presence of deeply embedded young stars. Within the boundaries of Orion on the sky, the Milky Way shows a mixture of bright and dim features. Dense star fields lie behind some parts of the figure, while other directions intersect large clouds of gas and dust that dim the more distant background. The combination of foreground stars, intervening clouds, and background glow gives the region a layered structure where different physical components sit at different distances yet overlap along the line of sight. Surveys of the area in various wavelengths reveal an association of massive young stars spread over hundreds of light years, many of them still moving in related orbits within the spiral arm where they formed. These associations trace the recent history of star formation in this sector of the galaxy. The gas clouds that gave birth to them are shaped by the radiation and winds from the most massive members, as well as by past explosions of stars that have already reached the end of their lives. This feedback carves cavities and shells in the interstellar medium, compressing some regions while dispersing others, and in doing so influences where the next generations of stars will appear. Orion therefore marks not only a pattern on the sky, but also a genuine concentration of recent and ongoing star formation within the Milky Way's disk. Embedded within the constellation's boundaries is a particularly well-studied region of glowing gas and young stars, where ultraviolet radiation from hot, newly formed suns ionizes the surrounding hydrogen and causes it to emit a gentle diffuse light. Dark filaments of denser dust twist through this glow, silhouetted against the brighter background, while compact knots within the clouds host stars that are still in the process of gathering their final masses. Radio observations trace cold molecular gas that stretches beyond the bright nebulae, revealing long, sinuous structures that are invisible to the eye yet crucial to the story of how massive stars are assembled. All of this structure occupies only a small portion of the Milky Way's vast spiral arm, yet from Earth it fills a noticeable patch of the sky. The spiral arm itself, often called the local arm, extends for thousands of light years and contains not only the Orion complex but also many other star-forming regions, open clusters and isolated stars of many different masses and ages. The Sun and its planets orbit within this arm, sharing its general motion around the galactic center. As a result, the bright stars of Orion, the young clusters nearby, and the field stars scattered through the area all participate in the broader rotation of the galaxy, each following its own path around the center, while remaining part of the same large-scale structure. Over millions of years, their positions within the arm slowly change, and the patterns familiar to current observers will gradually distort. However, on the timescales of recorded human history, the constellation appears fixed, providing a stable frame of reference against the shifting conditions on Earth. Because Orion lies along a direction rich in bright stars and glowing clouds, it serves as a convenient reference region for studies of the Milky Way's disk. Astronomers use standard candles such as certain types of variable stars or star clusters with well-understood properties to estimate distances within and beyond the constellation. Combined with measurements of motion obtained through the Doppler effect, these distance estimates help map the shape and rotation of the local spiral arm. By studying Orion's gas clouds and young stars, researchers learn about the physical conditions that promote the formation of massive stars, the way those stars inject energy and matter back into their surroundings, and the balance between gravity and pressure that shapes the interstellar medium. Observations in X-rays reveal high-energy processes associated with young stellar objects and hot gas, while radio and submillimeter data trace the coldest components of the clouds. In this way, the constellation acts as a laboratory for understanding how a small part of the Milky Way functions. On a clear night, none of this complexity is directly visible without instruments, yet it underlies the simple, striking figure that stands out so easily to the eye. The bright rectangle, the short line of central stars, and the subtle background glow together represent a cross-section through a rich and active portion of the galactic disk, where star-birth, stellar evolution, and the sculpting of gas and dust all proceed on timescales far longer than any single human life. Orion within the Milky Way is therefore a gateway region, linking the familiar patterns of the night sky to the deeper structure and ongoing processes of the galaxy that surrounds the Sun and its neighbours. Within the familiar outline of Orion, one star in particular draws the eye with a steady warm glow that contrasts with the sharper whiter light of many of its neighbours, and this star is Betelgeuse. It occupies a corner of the constellation's rough rectangle, marking what observers commonly describe as the shoulder or upper region of the figure, so that whenever Orion is high in the sky, Betelgeuse stands as a prominent anchor point on one side of the pattern. To an observer in a dark location, its colour appears distinctly tinted toward orange or red, especially when compared with the cooler white and blue stars that make up the belt and lower parts of the constellation. This difference in colour is not a trick of the atmosphere alone, although near the horizon, air turbulence and dust can deepen the hue. Instead, it reflects fundamental differences in the surface temperatures of the stars. Betelgeuse shines with a spectrum weighted more toward red and orange light, indicating that its outer layers are cooler than those of many hot blue stars nearby. Despite this cooler surface, it appears very bright in the sky, which tells astronomers that it must be intrinsically extremely luminous, emitting a great deal of energy over a broad range of wavelengths. When measured with modern photometric instruments, Betelgeuse ranks among the brightest stars in the night sky, though exact ordering can change because of subtle shifts in its output and the different sensitivities of human vision and detectors. Its gentle orange light can dominate the upper part of Orion, providing a strong colour contrast with a bright blue star that marks the opposite corner at the other shoulder. This pairing of a cool red star and a hot blue star in the same constellation offers a clear visual illustration that stars are not all the same even when they appear similar in size to the eye. The apparent brightness of Betelgeuse on the sky is only part of its story. To understand how luminous it truly is, astronomers need to estimate its distance from Earth, because an intrinsically faint star nearby can appear as bright as an intrinsically powerful star far away. For relatively nearby stars, including Betelgeuse, the most direct method is to measure parallax, the tiny shift in a star's apparent position, against more distant background objects as Earth moves along its orbit around the Sun. By tracking this shift over time with precise instruments, researchers can infer the star's distance using simple geometric relationships. In the case of Betelgeuse, such measurements refined with data from space-based observatories indicate that it lies at a distance of roughly several hundred light-years. A light-year is the distance that light travels in 1 year in a vacuum, so the glow that reaches Earth on any clear night began its journey centuries ago. This means that the star is observed as it was in a past era long before modern telescopes existed, and long before many events in recorded human history took place, even though on astronomical scales this delay is quite modest. Given this approximate distance and the measured brightness at Earth, astronomers can estimate the total amount of energy Betelgeuse emits. These calculations show that it radiates tens of thousands of times more power than the Sun despite a cooler surface. This high luminosity implies a very large surface area, and hence a radius far greater than that of the Sun. In angular terms, the star's disk is still tiny on the sky, but it is among the few stars large enough and close enough that specialized interferometric techniques can begin to resolve its apparent size. These methods combine the light from widely separated telescopes to achieve the resolving power of a much larger instrument, allowing astronomers to infer the star's diameter in angular units, and by combining this with the distance estimate its physical extent in kilometers. Results confirm that Betelgeuse's outer layers would, if placed at the center of the solar system, reach beyond the orbit of the inner planets, and possibly into the domain of the outer rocky worlds, depending on the exact radius adopted from current measurements. The precise values carry uncertainties, but the overall picture is clear. Betelgeuse is a very large, cool, and extremely luminous star that occupies a volume of space far exceeding that of the Sun. The light from Betelgeuse does not reach Earth unchanged. It passes through interstellar space filled with thin gas and fine dust grains that can alter the color and brightness to a small degree. Dust tends to scatter and absorb blue light more efficiently than red, a process that can make distant stars appear slightly redder and dimmer than they would in a perfectly transparent medium. However, in the direction of Betelgeuse, this effect is not strong enough to disguise its fundamental nature. Spectroscopic observations, which spread the star's light into its component wavelengths, reveal characteristic absorption features associated with molecules and atoms in its outer atmosphere, as well as patterns that indicate relatively cool surface temperatures compared with hotter blue stars. These spectra, combined with brightness and distance estimates, allow astronomers to place Betelgeuse on diagrams that relate stellar luminosity to surface temperature. There it occupies a region reserved for very large evolved stars that have expanded late in their lives, a clue to its advanced stage of evolution. Even without delving into its detailed internal structure, its position on such diagrams already signals that Betelgeuse is no longer a young star in a simple stable phase, but an object that has already undergone significant internal changes since its formation. In everyday observing conditions, an unaided eye cannot track fine details of this behavior, but long-term records and systematic measurements show that Betelgeuse does not shine with perfectly constant intensity. Over periods of months to years, its apparent brightness can drift within a certain range, sometimes standing out more strongly in the sky, and at other times appearing slightly subdued compared with its neighbours. These variations are modest enough that a casual observer might not notice them over short spans, especially given the changing conditions of Earth's atmosphere. But instruments that measure light precisely capture the star's variable nature clearly. The detailed physical causes of this variability involve complex processes in the star's outer layers, including large-scale convection and pulsation, and they build on the fact that the star is both very extended and relatively cool at its surface. Its colour, however, remains dominantly warm and reddish throughout these cycles, so that its identity as the orange star at the shoulder of Orion remains stable, even as its output subtly rises and falls. From the perspective of the wider Milky Way, Betelgeuse is only one star among many, yet in its local region it plays a distinctive role. Its brightness and colour make it a useful reference point for calibrating instruments and for teaching the basics of stellar classification. Its location near young hot blue stars in the same constellation highlights the variety of stellar types present in a single star-forming complex, from massive objects still in earlier phases of their evolution to older stars that have expanded and cooled. Its relative proximity allows detailed study with techniques that are difficult to apply to more distant stars of similar type, making it an important case for testing models of how large, cool, luminous stars behave. Whenever Orion rises, Betelgeuse shines as a clear example of such a star, its centuries-old light crossing the intervening space to add a softly coloured point to the pattern that marks this rich region of the Milky Way. To an observer beneath a clear night sky, the light of Betelgeuse arrives as a calm, steady presence, a soft orange point that seems to rest comfortably among the sharper, white and blue stars of Orion. Its glow is not harsh. It spreads just enough to give the impression of warmth without appearing diffuse, shaped by the way Earth's atmosphere bends and scatters incoming starlight. When the star stands high above the horizon, its colour appears most clearly a gentle reddish tint that distinguishes it immediately from the cooler hues of the belt stars and from the bright blue star at the opposite shoulder. In this elevated position, the air column between the observer and space is relatively thin, so the effects of scattering turbulence and dust are reduced, allowing the intrinsic character of the light to show more faithfully. As Betelgeuse sinks closer to the horizon, the path through the atmosphere lengthens, and additional scattering and refraction can deepen its colour and increase the apparent shimmering of its image. But these changes rest on top of the underlying qualities that the star already possesses. The human eye responds to this light in a way that depends on both brightness and colour. In low light conditions, the more sensitive rod cells dominate vision, favouring the detection of broad contrast rather than fine colour distinctions, so Betelgeuse may simply appear as one of the brighter stars in a dark field. Under slightly brighter conditions, when both rods and cone cells contribute, the orange tint becomes more apparent, especially when the star is compared directly with a nearby blue or white star. The eye naturally forms such comparisons, and Betelgeuse's location within a constellation rich in contrasting stellar colours makes these differences easy to notice. To move beyond subjective impressions, astronomers use instruments that record the intensity of light in a controlled and repeatable way. Photometers and modern electronic detectors attached to telescopes measure the light from Betelgeuse through filters that isolate specific ranges of wavelengths. By counting the number of photons detected over a known interval of time, and by comparing these counts with those from standard stars whose properties are well characterized, they can assign the star a magnitude in various bands of the spectrum. The magnitude system is a logarithmic scale in which smaller numerical values correspond to brighter objects, but in this setting, the exact numbers are less important than the relative relationships they encode. Through such measurements, Betelgeuse is placed among the brightest stars in the night sky, when viewed in visible light with a brightness that allows it to stand out even through some degree of atmospheric haze or light pollution. Beyond simple brightness, the same instruments can measure how the intensity of Betelgeuse's light changes with wavelength. This spectral energy distribution reveals that more energy emerges in the red and infrared parts of the spectrum than in the blue, consistent with a relatively cool surface temperature for a star. By comparing the observed distribution with theoretical curves that describe how idealized objects radiate at given temperatures, astronomers infer an approximate effective temperature for the star's outer layers. Although Betelgeuse is cooler than many hot blue stars, it remains far hotter than any familiar environment on Earth, with a surface temperature of several thousand degrees. The combination of this temperature, the measured brightness at Earth, and the estimated distance leads to the conclusion that Betelgeuse must be physically very large to account for the amount of light it emits. The apparent size of Betelgeuse on the sky is still extremely small. Even through ordinary telescopes, it appears as a point since the diffraction limit of most instruments, and the blurring effects of Earth's atmosphere smear the light into a tiny disk of brightness. To probe the actual angular size of the star, astronomers turn to interferometry, a technique that combines light from two or more widely separated telescopes. By carefully merging the signals and analyzing the resulting interference patterns, they can infer details about the brightness distribution across the star's face. For a few nearby and very large stars, including Betelgeuse, this method yields an estimate of the stellar diameter in angular terms. When this angular size is paired with the distance derived from parallax measurements, the physical radius of the star can be calculated. Although uncertainties remain due to the complex structure of the outer layers, the inferred radius is hundreds of times larger than that of the Sun, reinforcing the view that Betelgeuse is a highly expanded star with a vast surface area. The light of Betelgeuse also carries information about motion. As the star and the Sun orbit within the Milky Way, their relative movement along the line of sight produces a small shift in the wavelengths of spectral lines, a phenomenon known as the Doppler effect. By measuring this shift, astronomers can determine the component of Betelgeuse's velocity toward or away from the solar system. Combined with proper motion studies, which track the star's slow drift across the sky, over many decades, this information reveals that Betelgeuse, like all stars, is not fixed in space, but follows its own path through the galaxy. However, these motions unfold over timescales so long that the star's position within Orion's pattern remains essentially unchanged throughout recorded history. When light from Betelgeuse is dispersed by a spectrograph into a detailed spectrum, dark absorption lines and broader molecular features appear superimposed on the continuous glow. Each line corresponds to a specific transition in atoms or molecules in the star's atmosphere, and their strengths and shapes provide clues about temperature, pressure, and composition. In the case of Betelgeuse, the presence of molecular bands and the characteristics of certain metal lines confirm that the star's surface layers are cool enough for complex species to form and survive. Slight asymmetries in the lines can hint at large-scale motions in the atmosphere, such as rising and sinking currents of gas. Taken together, these spectral fingerprints paint a picture of an extended dynamic outer envelope, within which the light is generated and then modified before it escapes into space. The path from Betelgeuse to Earth is not empty, and the interstellar medium leaves a modest but measurable imprint on the star's light. Fine dust grains scatter and absorb some of the photons, particularly at shorter, bluer wavelengths. This process, called interstellar extinction, dims the star slightly and shifts its observed colour toward redder hues. By comparing Betelgeuse's observed spectral energy distribution with models of how a star of its type would emit light in the absence of dust, astronomers estimate the amount of extinction along the line of sight. In this case, the effect is moderate but not overwhelming, so the star's inherent red colour remains evident. Adjusting for this extinction allows a clearer view of the star's true luminosity and temperature, important for placing it accurately on diagrams that relate stellar properties. From the point of view of someone standing under the night sky, these physical processes, instrumental measurements, and model comparisons are hidden behind the simple impression of a bright orange star. Yet every photon that enters the eye or a detector has passed through the layers of Betelgeuse's atmosphere, through the sparse material of interstellar space, and through the air above the observer. Each carries consistent information about the star's output at the time it left its surface centuries ago. When large numbers of such photons are gathered and analyzed, they allow a stable and coherent picture of the star's basic observable properties to emerge. Betelgeuse's light, when treated in this way, becomes more than a point in a constellation. It becomes a measurable signal that encodes brightness, color, apparent size motion, and the influence of intervening matter. These carefully derived quantities set the stage for understanding Betelgeuse as more than a visual landmark in Orion, establishing the external framework of data within which deeper questions about its structure and life history can later be addressed. When astronomers describe Betelgeuse as a red supergiant, they place it within a broad framework that classifies stars by their temperatures, brightnesses, and evolutionary stages, and this term captures several key facts about what kind of object it is. In this scheme, stars are not treated as isolated points of light, but as physical bodies that follow certain patterns in how they shine and how they change over time. One of the most useful tools for understanding these patterns is a diagram that relates a star's intrinsic brightness to its surface temperature. When many stars are plotted on such a diagram, they do not scatter randomly, but gather along certain bands and regions. The most prominent band is known as the main sequence, where stars spend most of their lives steadily fusing hydrogen into helium in their cores. Above and to one side of this band lie zones where stars are both cooler at their surfaces and far more luminous overall, and it is here that red supergiants are found. A red supergiant is therefore a star whose surface is relatively cool compared with the hottest, bluest stars yet, which shines with an enormous total power output, because it has expanded to a very large radius. Its colour appears reddish, or orange, because its surface emits more energy at longer wavelengths, and its brightness indicates that its surface area must be vast. Such stars are not born in this state. They begin life as massive hot and bright objects on the main sequence, with surface temperatures far higher and colours shifted toward blue or white. In that early phase, their energy comes from the steady fusion of hydrogen into helium deep in the core, a process that releases enough power to counteract the inward pull of gravity and keep the star in hydrostatic balance. Over time, as hydrogen in the core is consumed and converted into helium, the central region's composition changes. When the supply of hydrogen there falls below a certain level, the balance that maintained the earlier state can no longer be held in exactly the same way. The core contracts and heats, while the outer layers respond by expanding and cooling. For stars of sufficiently high initial mass, this restructuring leads not merely to a modest swelling, but to an enormous growth in size, converting a compact hot star into one whose radius is hundreds of times larger than the Sun's. The surface cools as it expands because the same or greater energy is radiated from a much larger area, and the emergent spectrum shifts toward redder colours. In this way, a once blue or white star becomes a red supergiant. Betelgeuse, with its cool surface temperature, immense luminosity, and enormous radius, fits naturally into this class. Its position on the brightness-temperature diagram places it well above the main sequence in the region, occupied by highly evolved massive stars that have already exhausted the hydrogen in their cores and have reorganized their internal structures. The term supergiant distinguishes it from less massive red giants, which also show cool surfaces and expanded envelopes, but arise from stars with lower initial masses. In red giants, the total luminosity is typically lower and the evolutionary path differs in important details. Red supergiants, by contrast, come from stars that began life with many times the mass of the Sun, and this higher mass sets the conditions for more extensive internal changes and more powerful energy generation as the star advances through different stages. The outer appearance of a red supergiant is shaped by this history. Because the star has expanded so dramatically, its surface gravity is relatively low. Gas in the outer layers is only weakly bound compared with a situation in a smaller, more compact star. Convection, the bulk motion of rising hot material and sinking cooler material, becomes a dominant means of transporting energy through the envelope. This convection takes place on very large scales with giant cells that can cover significant fractions of the surface. The result is a photosphere that is mottled and dynamic rather than smooth and uniform. Observations of Betelgeuse with high-resolution techniques suggest the presence of bright and dark regions associated with these convective structures, although the details are still the subject of active study. The low surface gravity also means that gas can escape from the star more easily, feeding a slow but persistent outflow known as a stellar wind. This wind carries material away at speeds of several tens of kilometers per second, gradually removing mass from the star over long intervals of time. The gas cools as it flows outward, and dust grains can condense in the expanding envelope. Radiation from the star pushes on these grains, helping to drive them further into space. In this way, a red supergiant both contains the products of earlier nuclear reactions in its interior and actively returns some of that processed material to the surrounding interstellar medium. The composition of the outer layers, as revealed by spectral lines, often shows signatures of this internal processing, since convection can dredge up material from deeper zones and bring it to the surface. Betelgeuse displays such signatures consistent with a history in which internal nuclear burning has already altered the abundances of certain elements. The classification of Betelgeuse as a red supergiant also implies certain things about its internal structure, even though those regions cannot be seen directly. Models of stellar evolution that follow the behavior of massive stars show that once the core hydrogen is depleted and the star has become a red supergiant, energy generation continues in different forms. Hydrogen fusion may persist in a shell surrounding an inert helium core, and at later stages additional shells of fusion of heavier elements can appear. The exact sequence and duration of these stages depend on the star's mass composition and mass loss history. For Betelgeuse, whose initial mass is estimated to be many times that of the Sun, these models indicate that it has already progressed beyond its simple main sequence phase. However, at the level of the outer appearance, what matters is that this internal complexity supports the expanded envelope and maintains the high luminosity that observers measure. The star's inclusion in the red supergiant category is therefore both a description of its current observable state and an indication that it occupies a particular phase in the broader life cycle of a massive star. When astronomers compare Betelgeuse with other red supergiants in the Milky Way and in nearby galaxies, they find both similarities and variations. Stars such as Antares and others in rich star-forming regions also show cool surfaces, large radii, strong mass loss, and position in the same broad area of the brightness-temperature diagram. Differences in mass-age composition and environment lead to different details in their behavior, such as the strength of their winds, the extent of their surrounding dust shells, and the patterns of their variability. Studying a population of red supergiants helps refine models of massive star evolution and constrains the physical processes in their interiors. Betelgeuse is especially important in this context because its relative proximity allows more detailed observations than are possible for many similar stars. Interferometric imaging, precision, spectroscopy, and long-term monitoring of its brightness changes all provide data that can be set against the predictions of theory. When these observations are interpreted within the framework of red supergiant evolution, they help improve the understanding of how massive stars behave in this expanded, cool, luminous phase. In everyday language, to call Betelgeuse a red supergiant is to say that it is a very large, relatively cool star that shines with a great deal of power and has already used up the simple main fuel that sustained its earlier life. Its orange-red colour, high luminosity, and huge radius all follow naturally from this description. Its membership in this class situates it among the most visually striking and physically interesting stars in the galaxy, not because it is unique in kind, but because it is a nearby and accessible example of a well-defined stellar type. With this classification in place, the next steps in understanding Betelgeuse involve examining how its enormous outer layers behave in detail, how its brightness changes over time, and how its mass loss shapes the environment around it all within the calm, structured picture provided by the concept of a red supergiant star. Seen through the lens of modern astronomy, the surface of Betelgeuse is not a smooth, sharply outlined sphere, but a vast and restless region, where hot gas cooler patches and rising and sinking currents blend into a complex and shifting pattern. The word surface itself becomes approximate when applied to a star of this kind. In everyday terms, one might imagine a clear boundary between the inside and the outside, but in a red supergiant the outer layers are extended and diffuse, so that the passage from dense interior to thin outer atmosphere occurs gradually, rather than at a single well-defined edge. The layer from which most of the visible light escapes is called the photosphere, yet around and above it lie additional levels of gas that also contribute to the star's appearance and behaviour. In Betelgeuse, the photosphere is cool enough that molecules can form in significant numbers, and the presence of these molecules imprints recognisable patterns on the spectrum. The temperature of this region, although described as cool by stellar standards, still reaches several thousand degrees, but the low surface gravity and great radial extent mean that the gas is relatively tenuous. Energy produced deeper inside reaches this outer layer, in part through convection, the physical movement of gas that carries heat outward. In a red supergiant, convection does not consist of small fine granules as seen on the Sun, but of enormous cells that can span a large fraction of the visible disk. Hot gas rises in broad plumes from deeper layers, transporting energy toward the photosphere where it radiates away into space. As the gas loses heat, it becomes cooler and denser, and begins to sink, completing the convective cycle. Because these cells are so large and their lifetimes can be comparable to, or longer than, the time it takes the star to rotate the visible surface, is mottled with bright and dark regions that change only slowly on human timescales. Interferometric observations of Betelgeuse, which combine light from widely separated telescopes to reconstruct the shape of the star, support this picture by revealing asymmetries and irregularities in the brightness across its face, consistent with the presence of large convective structures. These patterns mean that the concept of a uniform featureless disk is too simple. Instead, the photosphere is a dynamic landscape shaped by rising and falling currents of gas. Above the photosphere, the atmosphere of Betelgeuse extends outward over many stellar radii, forming a series of layers that gradually merge into the surrounding circumstellar medium. In these outer regions, the gas becomes cooler and more rarefied, and conditions allow the formation of a variety of molecules and dust grains. This extended atmosphere is sometimes described as a molecular envelope, indicating that it contains complex species that cannot survive in hotter regions closer to the core. Spectral observations in infrared and radio wavelengths detect emissions from these molecules, providing evidence for the structure and composition of the material around the star. The density in these layers is low by terrestrial standards, yet the sheer volume of space involved means that the total mass contained in the atmosphere and surrounding envelope is significant. At the same time, the low surface gravity allows gas to escape relatively easily. The combination of convective motion pulsation of the outer layers and radiation pressure on dust grains leads to a slow but persistent stellar wind that flows outward from Betelgeuse. This wind is not a uniform stream, but can vary in density, speed, and direction, creating clumps, arcs, and filaments of gas and dust that move away from the star over time. Observations in infrared light reveal these structures as faint extended features surrounding Betelgeuse, sometimes forming partial shells or bow-shaped arcs, where the outflow interacts with the interstellar medium. In this way, the star's atmosphere is not confined to a narrow shell, but grades into a complex three-dimensional environment that stretches far beyond the photosphere. The lack of a sharp boundary is also evident when astronomers try to define a single radius for Betelgeuse. Because the outer layers are so diffuse and dynamic, different observational techniques can yield slightly different values for the apparent size depending on which wavelength is used and which depth of the atmosphere is being probed. Measurements in visible light tend to sample the deeper, hotter layers closer to the traditional photosphere, while near-infrared observations may pick up additional contributions from overlying molecular gas. As a result, the star can appear somewhat larger in some bands than in others. The choice of a radius, therefore, depends on a convention about where to draw the line between the star and its atmosphere, rather than on a physically sharp cutoff. This situation contrasts with more compact stars where the photosphere is thinner and the density drops rapidly enough that the radius is easier to define. For Betelgeuse, the gradual decline in density and the presence of extended material make any simple statement about its size an approximation. The atmosphere of Betelgeuse also shows signs of motion beyond simple convection. Spectral lines formed in different layers exhibit subtle shifts and asymmetries that indicate bulk flows of gas shocks and perhaps localized eruptions. These features suggest that the outer layers are subject to waves and oscillations that carry energy and momentum outward. Some of these motions may be connected to the variability in Betelgeuse's brightness over time, since changes in the structure and temperature of the atmosphere can alter the amount of light that escapes in different directions. Long-term monitoring of the star's spectrum and brightness reveals multiple overlapping cycles, some associated with radial pulsations, in which the entire outer shell expands and contracts, and others likely linked to the evolution of a large convective cells. In all cases, these processes underline the fact that the atmosphere is not static. It is a changing dynamic region where gas responds to internal driving forces and to its own radiative losses. At greater distances from the star, where the outflowing wind has cooled further, dust grains condense from the gas. These grains are made of elements such as oxygen, silicon, and iron that have been synthesized in earlier stages of the star's life and brought to the surface by convection. Once formed, the grains absorb and scatter the star's light, heating up and re-radiating energy in the infrared. This makes the dusty envelope around Betelgeuse visible to instruments sensitive to those wavelengths, even though it remains invisible to the unaided eye. The distribution of dust is not uniform. Images reveal clumpy asymmetric structures that testify to the irregular nature of the mass loss. In some directions, the wind may be stronger or more heavily laden with dust, while in others it may be weaker or clearer. Over time, the continued outflow builds a shell of gas and dust around Betelgeuse that moves slowly outward into the surrounding interstellar medium. This shell carries with it material that has been processed inside the star, enriching the local environment with elements heavier than hydrogen and helium. Although the details of the mass loss rate and geometry are subjects of ongoing research, the general picture is that Betelgeuse is surrounded by an extended atmosphere that fades gradually into a circumstellar envelope, where gas and dust interact with both the star's radiation and the wider environment of the Milky Way's spiral arm. From a distance, this extended atmosphere and envelope do not alter the simple appearance of Betelgeuse to the naked eye, which still registers only a bright orange point. Yet when resolved and analysed with modern instruments, they reveal Betelgeuse as a star with a soft, ill-defined outer boundary, a mottled and dynamic surface, and a surrounding cloud of material shaped by convection, pulsation, and stellar wind. The term surface as applied to this star thus means the region from which most of the visible light emerges, but in reality there is no single crisp edge. Instead, there is a broad transition from dense light emitting gas through progressively thinner atmospheric layers, and then outward into the dusty envelope and the interstellar medium beyond. Within this transition zone, the observable properties of the star are set, and it is here in the interplay between the photosphere, the extended atmosphere, and the surrounding cloud that the externally visible face of Betelgeuse takes shape. Over time, the light of Betelgeuse does not remain perfectly constant, and this gentle instability is one of its most characteristic traits as a red supergiant. Careful observers over many decades have recorded small but real changes in how bright the star appears, both to the eye and to instruments. To someone glancing at the sky on one night, and then again on the next, these shifts are not obvious since they unfold over weeks, months, and years rather than moments. Yet when individual measurements are plotted as a function of time, a pattern emerges in which Betelgeuse slowly brightens and fades within a certain range. This behavior places it among a class of stars known as variable stars objects, whose apparent or intrinsic luminosities change with time for physical reasons, rather than because of any external obstruction. For Betelgeuse, the variability is of a semi-regular type. That is, the star shows preferred timescales on which its brightness tends to rise and fall, but these cycles are not perfectly periodic like the ticking of a clock. Instead, they drift and interact, producing a light curve that contains overlapping rhythms. Some of these cycles have lengths of several hundred days, while others may span a few years. The amplitude of the changes is moderate at its brighter phases. Betelgeuse can rank among the most luminous stars in the night sky, while at its fainter phases it slips a few steps down the list, though it remains prominent within Orion. These shifts expressed in the magnitude scale correspond to intensity changes large enough to be detected by instruments and under good conditions by experienced observers comparing the star with its neighbours. The recording of these variations has a long history. Visual observers using nothing more than their eyes and charts of comparison stars have estimated Betelgeuse's brightness for many years, building up a record that traces its behaviour across multiple cycles. In more recent decades, electronic detectors attached to telescopes have added precise calibrated measurements that capture subtle details in the light curve. By combining these data sets, astronomers can analyze the star's variability in different wavelength bands, revealing that the amplitude and timing of the changes can depend on the part of the spectrum being observed. This dependence reflects the fact that different layers of the star's atmosphere contribute differently to the light at different wavelengths, and that those layers respond in distinct ways to the physical processes driving the variability. One key contributor to Betelgeuse's changing brightness is pulsation of its extended envelope. In this context, pulsation means a global breathing motion in which the outer layers of the star alternately expand and contract. When the envelope swells, the surface area increases and the temperature may drop slightly. When it contracts, the surface area decreases and the temperature may rise. Because the energy output from deeper inside remains roughly steady on these timescales, the redistribution of that energy over a changing surface area alters the amount of light emitted at different wavelengths. As a result, the star's apparent brightness as seen from Earth shifts in a way that reflects both geometric and temperature changes. The extended nature of a red supergiant's envelope, with its low density and strong sensitivity to internal pressure and temperature variations, makes it prone to such pulsations. The presence of large convective cells at the surface further complicates the picture. These cells, where hot gas rises and cooler gas sinks, alter the local brightness across the star's face. If a particularly bright upwelling or a cooler darker patch occupies a significant fraction of the visible hemisphere, it can change the integrated light that reaches Earth. Because these convective structures evolve over time, their contribution to the overall variability is not strictly periodic. In Betelgeuse, the combination of pulsation and convection produces a light curve that contains both quasi-regular variations and more irregular fluctuations. As the star brightens and fades, its color also changes subtly. During phases when the outer layers are slightly hotter, more light may be emitted at shorter wavelengths, making the star's spectrum marginally bluer, while cooler phases favor longer wavelengths and a slightly redder appearance. These shifts are small enough that they do not alter the star's general identity as an orange-red object, but instruments sensitive to color indices can detect them. Spectroscopic observations taken at different times show that certain molecular bands and atomic lines strengthen or weaken in step with the brightness changes, indicating that the temperature and density structure of the atmosphere is evolving. For example, lines sensitive to temperature may deepen when the star cools and shallow when it warms, while lines formed at specific depths in the atmosphere may shift in shape as gas moves outward or inward. These detailed spectral variations provide a complementary view of the variability linking changes in the total output of light to physical motions and temperature changes within the outer layers. In addition to these gradual cycles, Betelgeuse has shown episodes in which its brightness deviates more strongly from typical patterns. In one such period, the star dimmed to an unusually low level compared with its long-term behavior, drawing increased attention from the astronomical community. During this episode, observers across the world recorded a substantial decrease in brightness over a timescale of months, bringing the star to a visual level noticeably fainter than its usual minimum. Because Betelgeuse is both prominent and well-studied, this event prompted intensive monitoring across many wavelengths. Observations indicated that the dimming was not due to a fundamental change in the star's total energy output alone. Instead, evidence pointed toward a combination of factors, including changes in the distribution of surface temperature and the formation or rearrangement of dust in the star's vicinity. If a large convective cell on the surface cooled and darkened a substantial area, it could reduce the amount of light escaping in certain directions. At the same time, if a burst of material from the atmosphere condensed into dust along the line of sight, that dust could absorb and scatter light, further reducing the observed brightness. Infrared data, which are less affected by dust than visible light, and high-resolution imaging of the region round the star supported the idea that localized dust clouds played a role. As time passed, the star's brightness gradually returned toward its more familiar range, suggesting that the underlying stellar structure remained intact, and that the extraordinary dimming resulted from transient atmospheric and circumstellar changes rather than from a permanent shift in the star's state. Events of this kind highlight the complexity of the processes at work in the extended atmosphere of a red supergiant. They show that the line between purely intrinsic variability and the effects of material outside the photosphere is not always sharp. In practice, the brightness seen from Earth reflects the combined influence of pulsations, convection, atmospheric structure, and dust formation, all of which can change on different timescales. Long-term monitoring is therefore essential for building a comprehensive picture of Betelgeuse's behavior. Over many decades, such monitoring reveals that despite occasional notable episodes, the star maintains a general pattern of semi-regular variation around an average brightness. This average has remained broadly consistent, indicating that the total energy output of the star does not wander wildly on these timescales. Rather, the visible changes trace adjustments in the outer layers and surrounding material. For researchers, the variability of Betelgeuse is not merely a curiosity. It provides a valuable diagnostic of the physics of its envelope and wind. By studying how brightness changes correlate with spectral features, radial velocity measurements and infrared emission from dust, astronomers can refine models of how energy and matter move through the extended atmospheres of red supergiants. The star thus serves as a laboratory for testing theories of stellar pulsation convection and mass loss in a regime where direct spatial resolution is becoming possible but remains challenging. At the same time, for observers under the night sky, Betelgeuse continues to appear as the familiar reddish star at Orion's shoulder, its long-term shifts in brightness gentle enough that they rarely disturb the overall impression of the constellation. The combination of relative stability in its role as a sky landmark and subtle, scientifically rich variability in its detailed behavior makes Betelgeuse a particularly useful example of how a star can be both reassuringly constant in appearance and quietly dynamic in its physical state. Around Betelgeuse, the extended atmosphere does not simply hover in place. It flows steadily outward as a continuous stellar wind that carries gas and dust away from the star and into the surrounding space. This outflow is one of the defining features of a red supergiant in its advanced stage and shapes both the environment close to the star and its longer-term evolution. The wind originates in the same outer layers that form the mottled photosphere and overlying atmosphere. There, convection, pulsation, and radiation all act together to push material outward. In the deepest parts of the envelope, convective motions lift gas toward the surface. Near the photosphere, pulsations cause the outer layers to expand and contract, sometimes giving parcels of gas enough additional energy and momentum to rise further than they otherwise would. As these layers lift and cool, conditions become favorable for the formation of molecules and then dust grains. Once dust condenses, radiation from the bright star exerts pressure on the particles because each grain absorbs and scatters some of the incoming photons. This radiation pressure pushes the dust outward, and in doing so it drags the surrounding gas along through collisions and interactions. The combined effect is a slow, dense wind that moves away from Betelgeuse at speeds of several tens of kilometers per second, much slower than the fast, thin winds of hot blue stars, but carrying far more mass per unit time. The rate at which mass leaves Betelgeuse through this wind is small compared with the total mass of the star in any single year, yet over long periods it becomes significant. Estimates based on observations suggest that the star sheds an amount of material each year that may be comparable to a fraction of the Sun's mass over 1 million years, so that over several 100,000 or a few million years, the cumulative loss can amount to a substantial share of the original mass. This continuous peeling away of the outer layers alters the star's structure and affects how its interior evolves, because mass is a key parameter in determining the balance between gravity and pressure. As Betelgeuse loses material, its envelope becomes lighter, its surface, gravity decreases further, and the conditions that sustain the wind are reinforced. In this way, the mass loss and the structure of the outer layers are connected in a feedback loop. From the outside, the consequences of this wind are visible in the form of a circumstellar envelope of gas and dust surrounding the star. Infrared observations reveal a glow from warm dust grains that absorb Betelgeuse's light and re-emit it at longer wavelengths. This emission traces arcs, clumps, and shells of material that have flowed out over different epochs. In some images, the envelope shows nested structures like partial rings, representing periods when the mass loss may have been stronger or weaker, or when the outflow was directed more in some directions than others. Radio observations detect molecular lines from gas in the envelope, providing information about its temperature, density, and motion. The gas expands outward roughly in a spherical pattern on average, but with clear signs of asymmetry and inhomogeneity that echo the irregularities seen closer to the star's surface. The relative speeds and distances of these structures allow astronomers to estimate how long ago certain features were ejected, building a time history of Betelgeuse's mass loss over thousands of years. At greater distances still, where the expanding wind meets the ambient interstellar medium, additional structures arise. Betelgeuse moves through the Milky Way's gas and dust along its orbit, and the interaction between its wind and the oncoming interstellar material creates a kind of bow-shaped region where the pressures balance. This bow structure visible in certain infrared images marks the frontier where the star's influence through its wind fades into the broader environment of the spiral arm. Inside this frontier, the gas and dust carry the imprint of the star's history, while outside it, the interstellar medium retains its own patterns shaped by other sources. The presence of such a bow indicates both the motion of Betelgeuse through space and the strength of its wind. Closer in, the wind modifies the way light from the star reaches observers. As gas and dust move outward, they can temporarily lie along the line of sight, attenuating or scattering some of the light. If the mass loss in a certain direction is enhanced during a given period, the resulting cloud can produce a localized dimming in visible wavelengths, even if the intrinsic luminosity of the star remains the same. The unusual dimming episode that drew attention to Betelgeuse in recent years fits naturally into this framework as a case where a fresh concentration of dust along the line of sight combined with surface changes to reduce the observed brightness. Over time, as the dust continues to flow outward and dilute its effect on the line of sight diminishes. In this way, the stellar wind not only shapes the long-term structure of the circumstellar environment, but also contributes to shorter-term fluctuations in the star's appearance. The composition of the material carried by the wind is another important aspect. Betelgeuse's interior has processed hydrogen into helium and produced other elements through nuclear reactions. Convection and mixing bring some of this processed material to the surface, altering the abundances in the outer layers. When the wind carries this gas away, it injects helium and heavier elements into the surrounding interstellar medium. Dust grains formed in the outflow incorporate elements such as oxygen, carbon, silicon, and magnesium. As the wind continues, it enriches the local environment with these products of stellar nucleosynthesis. Later, when the gas and dust mix with the wider interstellar medium, they become part of the raw material from which new stars and planets may eventually form. Betelgeuse's wind is therefore not only a feature of its own life cycle, but also a contributor to the chemical evolution of its region of the Milky Way. The detailed physics of the wind remains an active area of research. Questions about how exactly pulsations, convection, magnetic fields, and radiation pressure combine to drive the mass loss are studied through both observations and numerical models. High-resolution spectra taken over time track changes in line profiles that signal accelerating gas. Polarimetric measurements which detect the preferred orientation of scattered light reveal information about the geometry of the dust distribution. Interferometric imaging at different wavelengths maps the inner regions of the outflow where gas is just beginning to detach from the star. Each method provides a piece of the puzzle, and together they support the picture of a complex structured wind that varies over time but maintains an overall flow of mass outward. For the internal evolution of Betelgeuse, the cumulative effect of this mass loss is crucial. Massive star models show that how much mass a star retains in its envelope as it advances through later nuclear burning stages strongly influences its internal temperature and density structure. While the exact details of Betelgeuse's interior remain hidden from direct view, the observed strength of its wind sets constraints on how quickly its outer layers are being removed, and therefore on how its mass and radius are likely to change in the future. Even without specifying the ultimate outcome, it is clear that the star is not static. It is gradually shedding part of itself into space, building a rich circumstellar environment of gas and dust that records its recent history. This environment, shaped by the interplay of convection, pulsation, radiation, pressure, and interaction with the interstellar medium, forms a kind of outer cocoon around Betelgeuse. Within this cocoon, the star continues to shine with its distinctive orange light, while the material it has lost drifts outward, cooling, clumping, and slowly merging with the wider fabric of the Milky Way's spiral arm. Around Betelgeuse, the gas and dust carried outward by the stellar wind form an extended environment that stretches far beyond the star's already vast photosphere, creating a subtle halo that only reveals its structure when examined with sensitive instruments. To the unaided eye, none of this is apparent. Betelgeuse still appears as a single point of orange light. However, when telescopes equipped for infrared radio and high-resolution imaging study the region, the simple point source gives way to a complex network of shells, arcs and knots of material, each feature representing matter that left the star at a different time. In infrared observations, warm dust grains that have absorbed the star's radiation and re-emitted it at longer wavelengths trace out faint curved structures around Betelgeuse. Some of these structures appear as partial rings or arcs offset slightly from the star and differing in brightness and thickness. They can be thought of as snapshots of the outflow at specific distances, each one containing gas and dust that was ejected in a past episode of stronger or more focused mass loss. Because the wind expands at a roughly steady speed once it has left the immediate vicinity of the star, the distance of a given shell from Betelgeuse corresponds to the time that has passed since the material was released. In this way, the envelope preserves a layered record of the star's recent history, with inner shells containing younger material and outer shells holding older ejecta. The arcs are not perfect circles. They often show clumps and irregularities, suggesting that the wind is not uniform in all directions or at all times. Instead, some regions of the surface may drive stronger outflows than others, or pulses of mass loss may be concentrated along certain directions. Convection and pulsation in the outer layers can create localized enhancements in density and velocity, which then emerge as denser knots and filaments in the circumstellar environment. Over time, these structures expand and evolve, but their basic shapes can persist long enough to be seen in detailed images. In some directions, the shells appear brighter or more sharply defined, perhaps, because the wind has encountered denser interstellar gas there and compressed into a thinner layer. In other directions, the emission is more diffuse, tracing a more gentle interaction with the surroundings. Radio and submillimeter observations add another layer of information, revealing the presence of molecules such as carbon monoxide and other species in the gas around Betelgeuse. These molecules emit radiation at characteristic wavelengths, when they change rotational or vibrational states, and by mapping these emissions, astronomers can follow the distribution and motion of the gas. Spectral lines from the molecules are shifted in frequency depending on whether the gas is moving toward or away from the observer, so a detailed analysis produces a three-dimensional picture of the flow. In Betelgeuse's case, such studies show gas expanding outward at speeds consistent with a slow, dense red supergiant wind, with some asymmetries that mirror the irregularities seen in the dust distribution. The combination of dust emission and molecular line maps paints a coherent picture of an envelope that is both roughly spherical on large scales and patchy on smaller scales. At larger distances where the wind has travelled far from the star, the interaction with the interstellar medium becomes more prominent. Betelgeuse moves through the galaxy with its own space velocity, and as its wind pushes into the oncoming gas and dust, a bow-shaped structure can form ahead of the star in the direction of motion. Infrared images show such a bow as a faint curved arc that lies some distance from Betelgeuse, with the convex side facing the direction of travel. Inside this arc, the wind material is slowed and compressed as it meets the interstellar medium, while outside it the ambient gas flows past only moderately disturbed. The position and shape of the bow reflect the balance between the ram pressure of the wind and that of the surrounding medium, as well as the relative speed of the star. In some cases, additional fainter arcs are seen even further out, indicating earlier phases of interaction. The space between the star and the bow is filled with the layered shells of gas and dust created by the wind over many thousands of years. Closer in, where the dust has only recently condensed and is still comparatively warm, the envelope glows more brightly in the infrared. This inner region can show particularly complex structure, including asymmetric plumes of dust that extend away from the star along preferred directions. High-resolution imaging has revealed features that look like streams or jets of material, although their exact nature is still under study. These plumes likely emerge from localized areas on the stellar surface where convection pulsation or magnetic effects enhance the mass loss. As they travel outward, they cool and fragment, adding to the clumpy texture of the circumstellar environment. Embedded within this dust are gas components that can be traced by molecular lines, confirming that the plumes are part of the same overall outflow. The temperatures in the envelope decrease gradually with distance from Betelgeuse. Close to the stardust grains can be heated to several hundred degrees, radiating strongly at mid-infrared wavelengths. Further out, the grains cool to tens of degrees, shifting their emission to longer wavelengths. This temperature gradient, combined with the increasing volume of space at larger radii, produces a smooth decline in surface brightness from the inner to the outer parts of the envelope, with superimposed enhancements where shells or clumps concentrate the material. By modelling the observed emission at multiple wavelengths, astronomers can estimate the total mass of dust and gas in the envelope, the typical grain sizes, and the rate at which material is being added by the star. These models must account for the absorption and scattering of Betelgeuse's light by the dust, as well as for the re-emission of energy at longer wavelengths. The envelope also influences the appearance of the star itself when seen in certain bands. In visible light, the direct path from the photosphere to the observer is mostly clear, although temporary dust formations along the line of sight can cause extra dimming events. In the near-infrared, where dust absorption is lower but still significant, the envelope can contribute scattered and emitted light that slightly changes the observed brightness profile. At even longer wavelengths beyond those visible to human eyes, the star's own photospheric emission becomes relatively less dominant, and the dust emission can form a bright halo around the location of the star. These effects are taken into account when separating the pure stellar signal from that of the surrounding environment, so that the properties of Betelgeuse and its envelope can be studied both together and separately. The gas and dust around Betelgeuse do not remain forever in a compact region. As the wind flows outward and the star continues its motion through the spiral arm, the envelope gradually disperses and mixes with the interstellar medium. The shells and arcs that are visible now will over longer timescales fade as their material spreads out, and their contrast with the background decreases. In the nearer term, though, they stand as tangible traces of mass that was once part of the star's outer layers. Some of this material contains elements that were formed inside Betelgeuse through nuclear reactions and then brought to the surface by convection. As it joins the general interstellar medium, it adds to the pool of enriched gas and dust from which new stars and planetary systems may eventually emerge. Thus, the gas and dust surrounding Betelgeuse link the internal processes of a single, massive star to the broader cycle of matter in the Milky Way's disk. For now, this circumstellar environment forms a quiet, extended halo around the bright orange point seen in Orion, an envelope shaped by the star's wind, sculpted by its motion through space, and preserved as a layered archive of its recent activity. Before Betelgeuse shines as a bright orange point in Orion, it begins as part of a much larger, colder structure in the Milky Way, a giant cloud of gas and dust that drifts quietly within one of the galaxy's spiral arms. This cloud is made mostly of hydrogen and helium, with a smaller fraction of heavier elements and fine dust grains mixed in. Its temperature is only a few tens of degrees above absolute zero, so low that hydrogen atoms often combine into molecules, and the dust grains radiate faintly in the far infrared. From a distance, the cloud blends into the general structure of the spiral arm, but radio and infrared observations reveal filaments, clumps and knots within it, where gravity and pressure play out their slow contest. In such a cloud, the gas does not remain perfectly smooth. Turbulent motions stir it, and previous generations of stars influence it. Winds from hot, massive stars expanding bubbles of gas around them, and shock waves from earlier stellar explosions all sweep through the interstellar medium, compressing some regions and dispersing others. Where the gas is compressed, the density rises. If a particular clump grows dense and massive enough, gravity begins to dominate over internal pressure and magnetic support. In these places, the cloud starts to contract under its own weight. The region that will eventually give rise to Betelgeuse sits within one of these denser zones, part of a broader star-forming complex in the direction that later appears to observers as the constellation Orion. As the clump contracts, it fragments into smaller cores, each of which can form one or more stars. Within each core, gravity pulls the gas inward, causing it to heat as it falls. In the central regions where the density becomes highest, a protostar takes shape. This early object is not yet a stable star in the usual sense. It is a growing, warming embryo of a star surrounded by a thick envelope of infalling gas and often by a rotating disk. Small amounts of rotation present in the original cloud core become more pronounced as the material collapses because angular momentum is conserved. The result is a system in which gas spirals inward through the disk, while some material may be ejected along the poles in collimated outflows or jets. These processes help the system shed angular momentum and allow mass to gather onto the young star. In the cluster containing the future, Betelgeuse, many protostars form more or less at the same time, each one competing for gas from the surrounding reservoir. Some grow only modestly before the local supply is cut off by radiation and winds from nearby massive stars that have already begun to shine. Others, positioned in regions of the cloud where gas is more abundant, or where the disruptive effects of neighbours are weaker continue to accrete material for longer. Betelgeuse belongs to this latter group. In its formative phase, it accumulates a mass many times greater than that of the Sun. The exact mass depends on the details of the collapse and accretion, but the outcome is a star that qualifies as massive in the language of stellar evolution, with a deep gravitational potential well and a core that reaches very high temperatures and densities. Inside the protostar, the gas is initially supported by a combination of thermal pressure and the internal energy released during contraction. As more material falls in, the central temperature rises steadily. Once the core becomes hot and dense, enough hydrogen nuclei begin to fuse into helium at a significant rate, releasing energy through nuclear reactions. At first, this fusion may be sporadic or confined to a small region, but as the protostar continues to accrete material and heat up, hydrogen burning becomes the dominant source of energy in the core. When the outward pressure from fusion balances the inward pull of gravity throughout the star, the object reaches a stable configuration. At this point, Betelgeuse arrives on the main sequence as a very hot luminous star. This transition from protostar to stable star takes place over a relatively short span of astronomical time, for a massive object on the order of a few 100,000 to a few million years, much shorter than the time such a star then spends in its stable hydrogen-burning phase. During the formation period, the surroundings change as well. Radiation from the newly born massive stars in the cluster, including the young Betelgeuse, ionizes nearby gas, carving out glowing cavities within the molecular cloud. These regions shine in visible light as emission nebulae, where hydrogen atoms excited by energetic photons emit characteristic lines as they return to lower energy states. The intense ultraviolet radiation and fast stellar winds from the hottest stars erode the remaining dense gas, halting further accretion onto many protostars and dispersing the cloud that gave rise to them. The cluster gradually emerges from its natal cocoon, with its member stars now visible against the background of the Milky Way. In this environment, Betelgeuse stands out by virtue of its high mass and intense luminosity. In its youth on the main sequence, it is not yet the cool orange star seen today, but a hotter, bluer object radiating strongly at shorter wavelengths. Its light and wind help shape the local interstellar medium, adding to the collective influence of its massive siblings. The cluster as a whole moves within the spiral arm orbiting the galactic center, along with the Sun and countless other stars. Over time, the gravitational pull of the galaxy and internal motions within the cluster cause the stars to drift apart so that the association becomes more diffuse. Some members may still be recognized as a group, while others wander more independently. Betelgeuse, with its high mass, evolves more rapidly than most of its lower mass neighbors, but in the earlier stages its internal structure is still dominated by core hydrogen fusion, and its outward appearance is that of a young luminous star. The remnants of the original molecular cloud do not vanish instantly. Filaments of colder gas may persist in the vicinity, and new generations of lower mass stars can continue to form in sheltered pockets. The radiation and winds from massive stars, however, gradually clear large cavities, leaving behind shells and bubbles of gas that are visible in various wavelengths. These features record the energy input from the cluster into the surrounding medium. In the case of the region now associated with Orion, multiple episodes of star formation and feedback from massive stars over many millions of years create a complex web of bubbles, ridges, and pillars. Betelgeuse participates in this pattern as one member of a broader population of massive stars that influence their environment from birth onward. The initial chemical composition of the gas that forms Betelgeuse reflects the history of the Milky Way up to that point. Earlier generations of stars have already enriched the interstellar medium with elements heavier than hydrogen and helium through winds and explosions. As a result, the cloud from which Betelgeuse forms contains a modest but important fraction of such heavier elements. These elements play a role in cooling the collapsing gas in forming dust grains, and later in shaping the star's opacity and internal energy transport. They also set the baseline for the abundances that will later be modified by internal nuclear processes as the star evolves. In this sense, Betelgeuse's birth is not an isolated event, but part of an ongoing cycle in which material processed by older stars is gathered into new ones, which then begin their own cycles of transformation. Once Betelgeuse reaches the main sequence, the rapid, dramatic episodes of accretion and envelope dispersal calm down. The star settles into a relatively steady state, in which the core quietly fuses hydrogen into helium while the outer layers radiate the energy into space. From the outside, this stage appears as a bright, stable star within a young association, contributing to the illumination of any remaining nebular material nearby. The path from cold molecular cloud to such a massive luminous star, though complex in its details, follows a general pattern, familiar to models of star formation: gravitational collapse of dense regions, growth through accretion, onset of nuclear burning, and emergence into a cluster environment where many stars share a common origin. Betelgeuse's later evolution into a red supergiant builds on this foundation, but in its beginnings it is simply one of the massive offspring of a dense cold cloud in the Milky Way's spiral arm assembled from gas and dust that have cycled through earlier generations of stars and now gather to form a new, short-lived but energetically important member of the galactic population. During the longest stable part of its life, Betelgeuse exists not as a cool, swollen red supergiant, but as a much more compact, hotter star on the main sequence, quietly fusing hydrogen into helium in its core. In this earlier phase, the star's internal structure settles into a balance in which the inward pull of gravity is matched by the outward push of pressure from hot gas and from the energy released by nuclear reactions. The mass that will later define Betelgeuse as a massive star is already present, gathered during the formation process from the surrounding molecular cloud. Because this mass is many times greater than that of the Sun, the gravity in the central regions is strong, compressing the gas to very high densities and raising the temperature to tens of millions of degrees. Under these conditions, hydrogen nuclei collide with enough energy to overcome their mutual repulsion and undergo fusion, combining to form helium, and releasing energy in the form of gamma-ray photons and energetic particles. In a star of Betelgeuse's mass, the dominant channel for this energy generation is a network of reactions known as the carbon-nitrogen-oxygen cycle, in which existing heavier nuclei act as catalysts to help convert hydrogen into helium more efficiently at high temperatures. The details of these reactions take place far beyond direct observation, but their overall effect can be calculated and incorporated into models of stellar structure. In the core, the rate of energy production adjusts to the conditions imposed by gravity and pressure, such that the star settles into a state where the energy generated by fusion each second is just enough to support the weight of the layers above. If the core were to produce too much energy, it would expand and cool slightly, reducing the fusion rate. If it produced too little, it would contract and heat, increasing the rate. This feedback keeps the core in a state of near equilibrium over long spans of time. Surrounding the core layers of gas transport the generated energy outward toward the surface. In massive stars like the young Betelgeuse, the inner regions are often dominated by convective motions, with hot gas rising and cooler gas sinking, while further out radiation carries energy through a more stable envelope, where photons scatter repeatedly off atoms and ions as they drift outward. The exact arrangement of convective and radiative zones depends on the star's mass and composition, but in all cases the transport of energy is continuous, linking the deep core to the outer layers. The photons produced in the core do not travel straight to the surface. Instead, they undergo a long sequence of absorptions and re-emissions, bouncing through the dense interior in a random walk that can take hundreds of thousands of years before any given quantum of energy finally reaches the photosphere and escapes as visible light. Despite this long journey, the outward flow of energy is steady on human timescales, and the star shines with a relatively constant luminosity while it remains on the main sequence. From the outside, this stage presents a star that is hotter and bluer than the later Betelgeuse seen as a red supergiant. The surface temperature during the main sequence phase is much higher, so the star radiates more strongly at shorter wavelengths, giving it a white or blue-white hue when seen in visible light. Its radius is much smaller than in the red supergiant phase, perhaps only several times the radius of the Sun rather than hundreds of times. But the high temperature and large mass combine to produce a luminosity many thousands of times greater than that of the Sun. In this state, Betelgeuse is a bright, massive main sequence star embedded within its young stellar association, contributing intense ultraviolet radiation and fast stellar winds to the surrounding environment. Those winds and photons help shape the nearby gas-carving cavities in the residual molecular cloud, and influencing the conditions under which lower mass stars and planetary systems form. While this external activity proceeds, the core of Betelgeuse follows a slower, more patient evolution. Each fusion reaction converts a tiny amount of mass into energy, which flows outward and eventually escapes as light and other radiation. Over millions of years, the core's chemical composition changes as hydrogen is steadily consumed and helium accumulates. The balance between pressure and gravity adjusts gradually to this change. As helium, which is more massive per particle than hydrogen, becomes more abundant, the core contracts slightly and heats further. This contraction can increase the fusion rate, causing the star's luminosity to rise slowly over its main sequence lifetime. Models show that massive stars like Betelgeuse do not remain exactly constant even during this long, stable phase. Their brightness and temperature drift along characteristic paths on the brightness-temperature diagram. Nonetheless, compared with the more dramatic changes that come later, the main sequence stage is relatively calm and ordered. For Betelgeuse, this phase lasts only a few million to perhaps around 10 million years, much shorter than the multi-billion-year main sequence lifetimes of stars like the Sun. The reason lies in the strong dependence of fusion rate on temperature and mass. Because Betelgeuse is massive and hot, it burns through its hydrogen fuel much more quickly, even though it has more of that fuel to start with. The star can be thought of as a bright, short-lived engine, using up its core hydrogen at a high pace in order to support its large mass. Throughout this time, the outer appearance remains that of a luminous hot star, and the deeper restructuring of its interior proceeds out of sight. Inside the convective core, the mixing of material keeps the hydrogen supply relatively uniform, allowing the fusion process to use a large fraction of the core's mass before hydrogen becomes significantly depleted. Once the hydrogen abundance falls below a certain level, the balance that is held throughout the main sequence phase becomes harder to maintain. The core, now composed mostly of helium with only residual hydrogen, can no longer generate enough energy through hydrogen fusion alone to counteract the full weight of the overlying layers. Gravity therefore begins to win, and the core contracts more rapidly. This contraction increases the temperature and pressure beyond the levels present during the earlier main sequence stage, preparing the conditions under which new forms of nuclear burning can eventually begin. In response to the changes in the core, the outer layers of Betelgeuse do not remain unchanged. As the core contracts and heats, more energy flows into the surrounding envelope. The outer layers respond by expanding, and the surface temperature drops as the star's radius grows. The star moves away from its original position on the main sequence track and begins the transformation into the cool, enlarged state characteristic of a red supergiant. This marks the end of the main sequence phase of its life. Although the details of these transitions involve complex interactions between radiative and convective processes, nuclear reaction rates, and the equation of state of dense stellar matter, the broad outline is clear. Betelgeuse spends the longest stable part of its existence as a massive hot hydrogen-burning star with a convective core and a radiative envelope gradually converting the hydrogen in its core into helium while shining steadily with high luminosity. Only after this reservoir of core hydrogen is largely exhausted does the star move on to the more rapid and visibly dramatic stages of expansion and cooling that define its current red supergiant phase. As the long hydrogen-burning phase in the core of Betelgeuse draws toward its end, the star begins a gradual but profound change that will carry it from the hot, relatively compact main sequence state into the swollen cool configuration recognized as a red supergiant. Deep inside the core has been steadily enriched in helium as hydrogen nuclei fuse and release energy. Over time, the fraction of hydrogen in this central region falls while helium grows more abundant. When the supply of hydrogen in the core becomes too depleted to maintain the previous level of fusion, the delicate balance between pressure and gravity that has held for millions of years can no longer be preserved in the same form. Gravity starts to gain the upper hand in the core, and the central region contracts. As it contracts, the gas in the core is compressed to higher densities and temperatures. The rising temperature increases the rate at which any remaining hydrogen can fuse in a shell surrounding the contracting core, while the core itself moves toward the conditions under which helium can begin to fuse into heavier elements. At first, this contraction is moderated by the residual hydrogen burning in the core and in the emerging shell, but as helium accumulates and hydrogen dwindles, the core becomes more compact and more strongly bound by gravity. The contraction releases gravitational energy, which is converted into heat and partly radiated outward. This additional energy flows from the core into the surrounding layers, altering the structure of the envelope. In response to the increased energy input from beneath, the outer layers of Betelgeuse expand. The envelope, formerly more compact and hot, swells outward, increasing the radius of the star by a large factor. As the radius grows, the same or slightly greater total luminosity is now radiated from a much larger surface area. The effective temperature at the surface therefore drops, shifting the peak of the star's emission toward longer wavelengths. Where the young Betelgeuse once shone as a hot blue star, it now begins to take on a cooler, redder appearance. On diagrams that relate stellar brightness to surface temperature, the star moves away from the main sequence track, its marker drifting toward lower temperatures while remaining at high luminosity. The path across this diagram is not arbitrary. It reflects the changing balance between core contraction, shell burning, and envelope expansion. For a massive star like Betelgeuse, this movement can be relatively rapid on astronomical timescales, unfolding over a span of time that is short compared with the long hydrogen-burning life, but still vastly longer than any human lifetime. In the envelope, the expansion has several important consequences. The surface gravity decreases as the radius increases because the same mass is now spread over a much larger volume. This lower gravity makes it easier for gas to move, and convection becomes more dominant in transporting energy through the outer layers. Large convective cells develop, carrying hot gas upward and cooler gas downward over great distances. These cells create the mottled brightness pattern that characterizes the photosphere of a red supergiant and contribute to the irregularities in the star's light. The expanded envelope is also cooler on average, allowing molecules to form in the photosphere and above. These molecules imprint new features on the spectrum, marking the transition from a hot star dominated by atomic lines to a cool star rich in molecular bands. Spectroscopic observations of red supergiants, including Betelgeuse in its present state, reveal these molecular signatures, clearly confirming that the outer layers have cooled significantly compared with the earlier blue phase. At the same time, the lower surface gravity and the increased radius enhance the star's tendency to lose mass. Pulsations in the expanded envelope driven by interactions between radiation ionization zones and gas pressure can lift material to greater heights above the photosphere. As the gas rises and cools, dust grains can condense, and radiation pressure on these grains helps to accelerate them outward. Thus, the mass loss that was present to some degree in the main sequence phase becomes much more pronounced as the star inflates. In Betelgeuse, this intensified mass loss fills the surrounding space with gas and dust, building the circumstellar envelope and shells described in earlier sections. From the point of view of energy generation, the star is entering a more complex regime. Although the detailed structure of the core and the precise sequence of burning stages belong to the deeper interior, which will be examined more closely later, one broad fact is clear hydrogen fusion, once confined to the core, now continues in a shell around a helium-rich center. This shell burning contributes significantly to the outward energy flow and helps sustain the luminosity that supports the swollen envelope. As the core contracts and heats toward the threshold for helium burning, the star's outer layers continue to adjust. The overall luminosity may increase somewhat compared with the main sequence value, but the most striking change is in the surface temperature and radius. To an external observer equipped with instruments capable of measuring both brightness and color, Betelgeuse's evolution appears as a shift from a smaller, hotter, bluer star to a larger, cooler, redder, one that shines with comparable or greater total power. The cluster environment in which Betelgeuse was born also evolves during this transition. Many of the lower mass stars formed alongside it remain on the main sequence, changing only slowly over the same time interval. The hot, most massive stars in the association may already have left the main sequence before Betelgeuse, or may be undergoing their own transitions. The radiation and winds from these massive stars, including Betelgeuse itself, further sculpt the local interstellar medium, reinforcing the network of bubbles and shells begun in the earlier phases. As Betelgeuse swells into a red supergiant, its contribution to the cluster's feedback shifts from intense ultraviolet radiation to strong mass loss and mechanical energy carried by its slower, dense wind. From Earth, the transformation from a blue progenitor to the present orange-red star is not observed directly because it unfolds over time scales, many orders of magnitude longer than human historical records. Instead, astronomers reconstruct this path by studying populations of stars at different stages in young clusters, and by comparing them with theoretical models of stellar evolution. In these models, a star with Betelgeuse's inferred initial mass moves rapidly from the main sequence into the red supergiant part of the diagram once core hydrogen is depleted, and it then spends a relatively short fraction of its total lifetime in this expanded cool state. Observations of Betelgeuse, now combined with its likely age and mass, fit this picture, indicating that the star has already completed its journey across the diagram and occupies the region characteristic of red supergiants. Internally, the contracting core and the surrounding shell-burning region provide the energy that maintains the large envelope. Externally, the star shows the hallmarks of this new phase: a vast radius, a cool photosphere rich in molecular features, strong convection, pronounced pulsation, and a dense, dusty wind. The transition itself is not a single event but a continuous readjustment in which different parts of the star respond to changing conditions to maintain a global balance. Gravity compresses the center nuclear reactions and shell-burning supply energy, and the envelope swells until a new equilibrium is reached. Once this equilibrium is established, Betelgeuse settles into its role as a red supergiant, with its outer layers now far from the core, and its observable properties altered in line with the physics of this expanded cool state. From this point onward, the story of Betelgeuse's evolution turns increasingly on the behavior of the inner regions that support the envelope, but the transformation from compact hot main sequence star to enormous cool red supergiant forms the essential bridge between its youthful life and the more advanced internal burning stages that lie ahead. Inside Betelgeuse, beyond the extended atmosphere and the cool mottled photosphere, the material is arranged in a layered structure that reflects the sequence of nuclear reactions that have taken place over the star's life so far. These layers do not form a rigid onion with sharp boundaries, but rather a set of zones where different elements dominate the nuclear energy generation or the chemical composition, separated by transition regions where conditions change gradually. At the center lies a dense core that has already been transformed by earlier phases of hydrogen burning. During the long main sequence stage, hydrogen in this central region fused into helium, leaving behind a core composed primarily of helium with traces of heavier elements. When core hydrogen became depleted, the core contracted and heated, and hydrogen fusion shifted outward into a shell surrounding the helium-rich center. As the contraction continued and the temperature climbed, helium in the core reached the conditions under which it can begin to fuse into heavier nuclei such as carbon and oxygen, through reactions that require much higher temperatures than those that sustain hydrogen burning. In a massive star like Betelgeuse, once helium burning is established in the core, hydrogen continues to fuse in an overlying shell, so that two distinct nuclear burning zones coexist: a helium-burning core and a hydrogen-burning shell. The energy released in these regions flows outward and supports the expanded envelope above. As the core processes helium into carbon and oxygen, its composition changes again, and the balance between gravity and pressure adjusts. The central density rises and the temperature increases further. At some point, conditions become suitable for carbon to begin fusing in a shell around the contracting core, while helium shell burning continues above and hydrogen shell burning persists still higher up. In this way, the star develops multiple burning shells stacked one above another, each one responsible for transforming a particular element into heavier products. The exact sequence and overlap of these stages depends sensitively on the star's mass, its initial chemical composition, and the rate at which it loses mass through winds. For Betelgeuse, detailed interior models calibrated to its estimated mass and luminosity indicate that it has at least passed through the phase of core helium burning and now hosts active shell burning. But the precise set of shells active at the present time remains uncertain because the interior cannot be observed directly. Instead, astronomers infer the likely configuration by matching observable properties such as surface composition, pulsation behavior, and luminosity with theoretical tracks for massive star evolution. In all such models, however, the general pattern is similar. Deep inside, a compact core contains the ashes of previous burning stages, surrounded by concentric shells, where helium, hydrogen, and at later times heavier elements undergo fusion. Above these shells lies the extended convective envelope that forms the red supergiant's outer layers. Within each burning shell, nuclear reactions take place under specific conditions of temperature and density. Hydrogen burning in the shell nearest the envelope proceeds at lower temperatures than helium burning in the shell below it. Deeper still, if carbon burning has begun, the required temperatures are higher again. As a rule, each successive stage of fusion involving heavier nuclei demands higher temperatures and yields energy over shorter timescales than the stage before. This means that the innermost regions of the star where the heaviest elements are processed change more rapidly than the outer shells. However, even these advanced burning stages remain slow when measured against human experience taking place over thousands or tens of thousands of years, so the structure of Betelgeuse's interior is stable from one human generation to the next. The boundaries between shells are not simple surfaces. Physical processes such as convection mixing driven by rotation and internal waves can transport material across these interfaces. In some zones, convection may fully mix the region, homogenizing its composition, while in others radiative transport dominates and the stratification remains more intact. The interplay between mixing and stratification is important because it affects how fuel and ashes are distributed, and therefore how the burning proceeds. In Betelgeuse, the envelope above the hydrogen burning shell is strongly convective, dredging up material from the vicinity of the shell and carrying it closer to the surface. This mixing alters the abundances seen in the photosphere, providing indirect evidence of the nuclear processes occurring in the interior. For example, certain isotopes associated with the products of hydrogen burning appear at enhanced levels in the outer layers of red supergiants, compared with unevolved stars, consistent with the idea that material processed in the shell has been transported outward. In the deeper interior, closer to the core, mixing processes may be more limited, but subtle transport can still occur, blurring the lines between idealized shells. The energy generated in the burning shells flows outward through a combination of radiation and convection. In regions where the opacity of the material is high, photons scatter many times, and radiation alone is inefficient at carrying the flux, so convection sets in with hot gas rising and cooler gas sinking to share the transport. In other regions where the opacity is lower, radiation can move energy outward more directly. The pattern of these zones depends on how temperature, density, and composition vary with radius. For Betelgeuse models suggest that the envelope above the hydrogen burning shell is largely convective, while regions closer to the core may have alternating convective and radiative layers, each adjusted to maintain the required flow of energy. The presence of multiple burning shells has another important consequence. It sets up a stratified chemical structure with lighter elements dominating the outer layers and progressively heavier elements concentrated toward the center. Far from the core, the envelope remains rich in hydrogen and helium, even though some processed material has been mixed in. Just below the hydrogen burning shell, helium is more abundant. Inwards of the helium burning region, carbon and oxygen become the principal constituents. At still greater depths, once more advanced burning stages have operated neon magnesium and heavier nuclei appear. This gradient in composition reflects the sequence of nuclear reactions that have taken place and records the star's internal history. Although the exact element distribution in Betelgeuse today cannot be measured directly, the general pattern is a robust prediction of the physics of massive star evolution. The timescales associated with each burning stage shrink as the star progresses through this sequence. The hydrogen burning phase lasts for millions of years, the helium burning phase for hundreds of thousands of years, and the later stages often span only tens of thousands or fewer. For Betelgeuse, whose age is already measured in millions of years, this means that it has likely already completed some of the slower burning stages, and may be in or approaching faster ones. However, the uncertainty in its exact mass and internal state leaves some flexibility in where it currently stands along this path. Observationally, what is clear is that the star's luminosity, surface composition, and variability are consistent with a massive red supergiant whose core has evolved beyond simple hydrogen burning, and whose energy output is supported by a combination of shell burning and core processes involving helium and heavier elements. The existence of multiple burning shells also influences how the core responds to changes in its own structure. When a burning shell exhausts its fuel, the region it powers cools and contracts, transferring more weight onto the layers below. This can trigger new burning stages deeper in, while outer shells adjust to the altered conditions. The star's interior thus evolves through a series of readjustments, each one redistributing energy generation among shells and the core. Throughout these changes, the envelope responds by altering its size, temperature, and convective pattern, but from the outside, Betelgeuse continues to present itself as a red supergiant, with broadly stable luminosity and colour on human timescales. In this way, a relatively calm external appearance coexists with a more intricate and evolving internal architecture. The present structure of Betelgeuse can therefore be pictured as a dense central core, whose composition reflects the ashes of earlier burning, surrounded by layers where helium, hydrogen, and possibly heavier elements undergo fusion in shells, all encased within a vast convective envelope that extends outward to the visible surface and beyond into the extended atmosphere and circumstellar envelope. Each layer plays its role in maintaining the overall equilibrium of the star, supporting the weight of the material above, and providing the energy that keeps the envelope hot enough to shine. The details of which shells are currently active, how rapidly they are consuming their fuel, and exactly how material moves between them remain constrained by models rather than direct measurement, but the layered shell structure itself is a robust feature of massive stars at this stage. For Betelgeuse, this inner configuration forms the foundation on which later changes in the core will build, even as the star's outward appearance remains that of a single orange point in the shoulder of Orion when seen from Earth's night sky. Deep in the centre of Betelgeuse, far beneath the extended convective envelope and the nested shells of nuclear burning, the core evolves toward a state that is markedly different from the simpler conditions of its youth. Each successive stage of fusion that has taken place, there has left behind its own ashes, gradually building a central region composed of heavier and heavier elements. After core hydrogen burning creates helium, and core helium burning builds up carbon and oxygen, later burning stages in massive stars can process these products into neon magnesium silicon and eventually nuclei in the iron group. Each of these stages requires higher temperatures and densities than the one before, and each proceeds over a shorter timescale. In a star of Betelgeuse's mass, the central temperature during advanced burning reaches values of many hundreds of millions of degrees, and the density becomes so high that matter behaves in ways unfamiliar from ordinary terrestrial conditions. Electrons, which at lower densities move relatively freely, become crowded into a highly compressed state known as electron degeneracy, where quantum mechanical effects provide a significant part of the pressure that resists further compression. In such a regime, pressure depends less on temperature than in a normal gas, so heating the core does not cause it to expand as readily as it would in earlier phases. As the core composition shifts toward heavier nuclei, particularly those around the iron group, an important change in the energy balance of fusion reactions occurs. Up to this point, fusion of lighter nuclei has released energy, helping to support the star against gravity. However, fusing nuclei heavier than those in the iron group does not yield energy in the same way. In effect, once the core is dominated by iron group elements, it can no longer gain energy by fusing them into even heavier nuclei. The nuclear processes that have sustained the star's interior for millions of years thus approach a point where they can no longer contribute additional support. During the advanced burning stages that precede this state, such as carbon-neon oxygen and silicon burning energy is still produced, but these phases occur in shells around the inner core and proceed relatively quickly compared with earlier hydrogen and helium burning. The luminosity of the star as seen at the surface remains broadly similar, because the energy generated deep inside continues to flow outward, but within the core the balance between gravity pressure and nuclear energy shifts steadily. At the same time, the core loses energy through another channel neutrino emission. At the extreme temperatures and densities present in advanced burning stages, various reactions produce copious neutrinos, elusive particles that interact very weakly with matter and escape almost unhindered. These neutrinos carry energy away from the core, effectively cooling it in a way that does not immediately raise the pressure, because they do not deposit their energy locally. As a result, the core must contract further to maintain support, driving the temperature and density even higher. This neutrino cooling becomes increasingly important as the core composition approaches the iron group, hastening the progression through the late burning stages. The overall effect is that the core evolves toward a highly compressed state, in which most of the pressure support comes from degenerate electrons, the temperature is extremely high, and the composition is dominated by nuclei that can no longer release energy through fusion. Above this core, a set of burning shells continues to operate, each contributing to the star's luminosity and helping to maintain the extended envelope. Hydrogen burns in an outer shell, helium in a shell beneath that, and depending on the exact stage, shells of carbon-neon oxygen or silicon burning may lie closer to the core. The energy released in these shells flows outward and supports the envelope in its red supergiant configuration, while the core itself carries most of the star's mass in a compact region. The mass of this inner core grows as fusion in the overlying shells deposits more iron group material into the center. In massive star models, the core mass approaches a critical value at which electron degeneracy pressure can no longer safely support it against gravity. This critical mass is of the same order as the mass that would characterize a white dwarf star, roughly around 1.5 times the mass of the Sun, although the exact value depends on the core's composition, rotation, and other physical details. For Betelgeuse, whose initial mass is several times that of the Sun, models suggest that the core can grow to this critical range as burning proceeds, but the precise current mass and composition of its core remain uncertain. They cannot be measured directly. Instead, they are inferred from the star's luminosity, surface abundances, and estimated age by comparison with evolutionary tracks. Nonetheless, the broad expectation from theory is that a star of this kind will eventually develop a dense iron group core that approaches the limit of what electron degeneracy pressure can sustain. As the core edges closer to this limit, it becomes more sensitive to subtle changes. A small increase in mass from continued shell burning, or a change in conditions that favors certain reactions, can alter the internal balance. At the temperatures present, high-energy photons can begin to disassemble some of the iron group nuclei into lighter components in a process known as photodisintegration. This process absorbs energy rather than releasing it, removing thermal pressure support. At the same time, electrons may be captured by protons in the nuclei, producing neutrons and neutrinos. These electron capture reactions reduce the number of electrons available to provide degeneracy pressure, weakening one of the core's main supports against gravity. The neutrinos produced escape, carrying away additional energy. Both effects encourage further contraction. As the core's support mechanisms are eroded in this way, gravity drives a more rapid inward motion. The inner regions start to collapse and the timescale for change shortens dramatically, compared with the earlier quasi-static evolution. The outer burning shells and the envelope responding more slowly cannot instantaneously adjust to this sudden loss of support. In theoretical models of massive stars, this stage marks the onset of core collapse, a dynamical event in which the inner core falls inward at a significant fraction of the speed of light, while conditions at the very center become extreme enough to change the nature of the matter itself. For Betelgeuse, this phase lies in the future, and the timing of when its core will reach such conditions remains uncertain. Estimates of how far along the star is in its advanced burning stages vary, because they depend on its exact mass rotation rate, internal mixing, and mass loss history, all of which carry uncertainties. Some models place it earlier in its shell-burning sequence, others suggest it may be more advanced, but all agree that the final approach to collapse once an iron group core of critical mass has formed will be rapid on an astronomical timescale unfolding over time intervals far shorter than the millions of years that characterized its earlier life. From the outside, however, even a star with a highly evolved core can continue to appear as a relatively steady red supergiant. The layered structure of burning shells and the extended envelope smooth out many of the internal changes so that the observable luminosity and color remain within a familiar range. Variability continues driven by pulsations, convection, and mass loss, but the overall classification of the star does not shift from one year to the next. The core conditions described by theory are therefore not directly visible. Instead, their presence is inferred from the combination of models and surface diagnostics. Betelgeuse's known properties indicate that it possesses the layered internal structure and dense core expected of a massive red supergiant well past its main sequence phase. As the core continues its slow progression toward heavier composition and higher density, the outer layers remain inflated and luminous, supported by the energy generated in the burning shells. The star thus presents a calm, familiar face in Orion's shoulder, while deep inside its core evolves along a path determined by the physics of nuclear reactions, degeneracy, pressure, and gravity, bringing it closer step by step to the conditions that in massive stars in general lead to core collapse and the explosive transformation that follows. From its current state as a luminous red supergiant in Orion, Betelgeuse belongs to a class of massive stars that, according to present models of stellar evolution, are expected to end their lives in core collapse supernovae. Yet the path from the dense inner core described earlier to that explosive outcome is governed by conditions that are both extreme and difficult to constrain precisely. Deep inside the core gradually approaches a composition dominated by iron group elements, supported mainly by the pressure of degenerate electrons. As burning in surrounding shells adds more material of this kind to the center, the core mass moves toward the critical range at which electron degeneracy pressure alone can no longer resist gravity. When that point is reached in a massive star, the inner core loses its ability to remain in static balance. Electron capture and photodisintegration remove pressure support while also carrying energy away, and gravity drives a rapid inward acceleration. The core collapses with the inner region falling nearly in free fall toward the center on a timescale of less than a second, compressing the matter to densities comparable to those found in atomic nuclei. Under these conditions, protons and electrons combine to form neutrons, and the core changes state, again becoming an extremely compact object dominated by neutron-rich matter. The collapse halts when the neutron-rich core becomes stiff enough to resist further compression, and the inner part of the core rebounds. A shock wave forms at the boundary between the rebounding inner core and the infalling outer core. At first, this shock stalls as it loses energy to the dissociation of nuclei and to copious neutrino emission, but in successful core collapse models, Neutrinos streaming out from the hot newly formed neutron. Rich core deposit enough energy in the region, behind the stalled shock to revive it. The revitalized shock then propagates outward through the infalling material. As it moves, it heats and accelerates the overlying layers, eventually unbinding them from the star. The result is a supernova explosion. The outer parts of the star are hurled into space at thousands of kilometers per second, while the central core remains behind as a compact remnant, likely a neutron star, or if the mass is high enough, a black hole. In such an event, the star's luminosity increases dramatically for a short period. The energy released in a core collapse supernova is immense, though most of it emerges in the form of neutrinos that pass through matter almost unhindered. A smaller but still enormous fraction appears as kinetic energy of the ejected material and as electromagnetic radiation. When observed from a distance, this radiation makes the star brighten by many orders of magnitude compared with its previous red supergiant phase. For a star located several hundred light-years away, as Betelgeuse is estimated to be such an explosion, would produce a transient object brighter than any ordinary star in the night sky. Models suggest that if Betelgeuse were to undergo a core collapse supernova in its current position, its peak brightness as seen from Earth could rival that of a crescent moon, and might be visible in daytime for some period, though the exact appearance would depend on details of the explosion and the intervening interstellar material. The light would rise over a period of days, remain near maximum for a time, and then decline over weeks and months as the expanding debris cooled and as radioactive isotopes forged in the explosion decayed. From the standpoint of present scientific understanding, such an event would not pose a known danger to Earth. The key reason lies in distance. At several hundred light-years, the inverse square law for radiation ensures that the intensity of high-energy photons and particles reaching Earth from the supernova would be spread over an enormous sphere. By the time any gamma rays or X-rays from the explosion reached the solar system, their flux would be far weaker than the levels associated with more nearby astrophysical sources or with the Sun's own activity. Earth's atmosphere provides substantial shielding against high-energy radiation arriving from space, absorbing and scattering photons before they reach the surface. The planet's magnetic field deflects many charged particles. Current models that examine the effects of a core collapse supernova at distances comparable to Betelgeuse's location indicate that while subtle changes in the upper atmosphere might occur, there is no clear mechanism by which such an explosion would cause catastrophic damage to the biosphere at this range. The gravitational influence of the supernova would also be negligible for Earth, since gravity depends on mass rather than luminosity, and the total mass of Betelgeuse is far too small and far too distant to perturb the orbits of planets around the Sun. In addition, much of the mass ejected in the explosion would move outward roughly symmetrically, and the remnant core, whether a neutron star or black hole, would carry only a fraction of the original stellar mass. For Earth, the event would be a striking change in the appearance of the sky, rather than a physical threat. The timing of when Betelgeuse will reach this core collapse stage remains one of the most prominent uncertainties in current discussions. Stellar evolution models place red supergiants like Betelgeuse in a phase that precedes core collapse by a relatively short interval on astronomical scales, perhaps on the order of tens of thousands to a few 100,000 years, depending on the star's exact mass rotation, internal mixing and mass loss history. However, within that broad window, present observations do not allow a precise prediction of when the critical core conditions will be met. The internal burning stages that lead up to collapse proceed at rates determined by core temperature and density, and while models give general timescales small uncertainties in the star's internal structure, translate into large uncertainties in the calendar time remaining. It is therefore scientifically correct to say that Betelgeuse is in a late stage of its evolution, and is expected at some point on long astronomical timescales to undergo a core collapse supernova. It is not currently possible to state whether that moment lies hundreds of thousands of years in the future, or closer, or whether the star is still in a relatively earlier shell-burning state with longer to go. The light seen from Betelgeuse today left the star several hundred years ago, so there is also the logical possibility that significant changes have already occurred in the intervening time that have not yet been revealed to Earth. Nevertheless, even taking this light travel time into account, the uncertainty in models is so large that the range of plausible explosion dates remains broad. Popular descriptions sometimes compress this wide range into the phrase that Betelgeuse may explode in human lifetimes. This expression reflects the fact that in principle, a core collapse supernova from Betelgeuse could occur at any time within the broad model window, including timescales comparable to human centuries, but it should not be interpreted as a specific forecast that such an explosion is likely within any particular decade or generation. From a scientific perspective, the correct statement is that Betelgeuse is an evolved massive star whose remaining lifetime before core collapse is uncertain by at least many orders of magnitude compared with the human lifespan, and that current observational data do not pin down the exact stage of its innermost burning with enough precision to narrow this significantly. If Betelgeuse were to approach core collapse, the first physical signal reaching Earth would probably be a burst of neutrinos. These particles, produced in large numbers when the core changes state stream out of the star almost unimpeded, because they interact so weakly with matter, they would pass through the envelope long before any shock-powered optical emission could emerge. Sensitive neutrino detectors on Earth, designed to monitor the low-level flux from the Sun, and other sources can detect bursts from supernovae in the Milky Way. In previous supernova events in neighboring galaxies, neutrino bursts have been recorded hours before the visible light peaked, providing early warning. For a future supernova from Betelgeuse, a similar burst would give astronomers a short advance notice that the shock was on its way to the surface. They could then observe the brightening in many wavelengths as the optical and ultraviolet emission ramps up, followed by the emergence of X-rays and gamma rays and the gradual evolution of the expanding remnant. Over years and decades after such an event, the supernova remnant would grow into a shell of gas and dust, rich in freshly synthesized elements, glowing in X-rays, optical lines, and radio waves as its shock front plows into the surrounding medium. That remnant would eventually blend with the complex web of gas and dust already present in Orion's region of the Milky Way, adding its contribution of heavy elements to the interstellar medium and shaping the local environment for future star formation. At present, however, Betelgeuse remains a red supergiant whose light reaches Earth as a steady warm glow at Orion's shoulder. Its internal core and shells are progressing through advanced burning stages that theory associates with an eventual core collapse, but the exact schedule of those changes cannot be read directly from current observations. The star's variability, mass loss and circumstellar structures all fit within the range expected for an evolved massive red supergiant. Its distance provides a comfortable margin of safety against harmful radiation effects from a future supernova, while still allowing the possibility that such an event, whenever it occurs, would be an impressive sight in Earth's sky, and a rich source of information about the physics of stellar death. In this way, Betelgeuse occupies a position in which it is both a familiar, stable landmark in the constellation Orion, and a member of a class of stars known from general principles of stellar evolution to be moving toward an eventual core collapse and explosion on timescales that remain long and uncertain compared with the span of human lives,